Hey, Tim DeStasio here. It's Psychrometric Saturday, and we have been talking for the past few weeks about enthalpy. And enthalpy, of course, is heat. It's a combination of sensible and latent heat. Now, we've also been talking about the uses of enthalpy in our industry, but we haven't covered one yet that we're going to cover today, and that is economizers. Economizers are a set of controls and dampers that we typically see in many commercial buildings, which allows the building to cool down using outside air when the outside air conditions are conducive to cooling the building down. Commercial buildings, because of their nature, sometimes have a cooling demand well down below the typical outdoor temperature that a residential building would stop really needing to cool down with air conditioning. So we could be in the 40s or 50s outside in a commercial building because of the people inside, the equipment, the machinery, maybe the solar loads on it. That building could still need air conditioning or cooling on down to those lower temperatures. And economizers are a way to cool the building without using the mechanical compressors, which saves energy and money. But we have to make sure that the outside conditions are actually conducive to cooling the building down. That's an exercise that we're going to do today. So an economizer is going to take a look at a few conditions. The first thing it's going to do is take a look at our target indoor conditions. So let's plot those first. We've got 70 degrees dry bulb, 55 degree dew point. So let's go ahead and plot that. We've got 70 degrees dry bulb and 55 degrees dew point. So we're going to plot that dot, and then we're obviously going to have to plot our enthalpy. And we're just going to put a line that runs parallel to our wet bulb lines, goes on in to our enthalpy scale. And what is our enthalpy? Well, it's 26.8 BTUs per pound. So that's our enthalpy line here. Now, essentially what we're looking for is whether or not outside conditions either have more enthalpy or less enthalpy than that line right there. If they have more enthalpy, then we're actually adding heat to the building. We're going in the wrong direction. First scenario that we're talking about is our outdoor temperature being 70 degrees dry bulb and 60 degrees dew point. So let's go ahead and plot that right now. So we go down to 70 degrees dry bulb and 60 degrees dew point. That puts us right here. And I think you probably already know where we're going with this, but we're going to go ahead and plot it right now. We're again going to draw a line parallel with our wet bulb lines. And as you can see here, we're at 28.9 BTUs per pound of enthalpy. It does not make sense for us to cool this building down, even though it is the same temperature outside that it is inside. We're simply going to be adding more heat because there's more moisture in the air. Now let's take another set of outdoor conditions. Let's say it's a cold winter day. It is 30 degrees dry bulb and 20 degrees dew point. Let's plot that and see whether or not it makes sense to cool with outside air there. And I think you probably know where that's going to lead us, but we'll go ahead and plot it. We've got 30 degrees of dry bulb and 20 degrees of dew point. So we're way over here in the extremity of our psychrometric chart. As you can see, we are well below our indoor enthalpy. And so in fact, we're so far below it, we're not even on the scale that I drew there. So we could definitely cool this building with these conditions. However, we need to be very, very careful because it is 30 degrees outside. And if we bring in raw 30 degrees air, we could do a lot of damage. We could have freezing situations. We could freeze pipes. We could have condensation. So the logic gives us a backstop, and that's called our mixed air low limit. So when we mix our return air and our outside air, we are going to look to make sure that we don't go below 53 degrees, which is usually the default setting on an economizer control. So we're not going to bring in 100% outside air. Rather, we're going to mix it with return air so it looks a little bit more like this. Still well below the enthalpy that we're trying to maintain inside, but we're not going to do damage. Now let's take a look at another set of conditions. Let's say that it is 55 degrees outside dry bulb and 55 dew point. Well, if you recall from a previous episode of Psychrometric Saturday, whenever these two numbers are the same, we are at 100% saturation, 100% relative humidity. It is probably raining outside. You may think, well, do I really want to bring all that moisture into the building? Well, let's plot it and see whether it makes sense. Our outdoor conditions were 55 degree dry bulb, 55 degree of dew point. So that puts us right here on the saturation curve. You can probably already see where I'm going with this, but we're going to go ahead and plot that enthalpy line. Again, we're going to plot this point. We're going to draw a line that crosses that point, but also runs parallel with our wet bulb lines. And we're down here 23 BTUs per pound of enthalpy. We're still considerably below our indoor enthalpy conditions, so it makes sense to cool the building even at 55-degree dry bulb, 55-degree dew point, 100% relative humidity. If you think about that, that's pretty close to our target supply air conditions when we're running air conditioning anyway. Let's take another set of conditions now. Let's say that it's 62 degrees dry bulb and 60 degrees dew point outside. Now, before we plot it, where do you think that might bring us? It is considerably cooler outside than it is inside, so it may seem like it's going to be conducive to cool the building with outside air. Let's go ahead and plot it and find out. So we're at 62-degree dry bulb and 60-degree dew point. That puts us right here, pretty much under the line that we've already drawn for our indoor conditions. So as we can see, we're not really moving the needle much. It would not make sense from an enthalpy standpoint to bring in that fresh air because we're actually adding to the heat, not taking it away. So even though that looked like that may help us, it doesn't. So that's the importance of knowing your enthalpy. And so modern economizer controls simply do not look at outdoor temperature to make a determination whether or not we should cool the building with outside air or not. They also look at humidity and they calculate what the enthalpy is. They compare it to the indoor enthalpy and see whether there is a net gain or loss. And obviously, if it gets really cold outside, there is a mixed air low limit so that we don't freeze pipe, cause condensation issues, and so forth. So if you're a commercial HVAC technician and you're starting up and commissioning commercial systems with economizers, it's important to know the enthalpy that you are shooting for. If you're in a dry climate, it may be one setting. If you're in a wet climate, it may be another. That's all we have to cover for this time. Thanks for joining us on Psychrometric Saturday.